Monica. I'm working with Aaron Dinner, David Byron, and Ron Levine, and this work is work that I've done with Aaron Dinner. And we're working in a cycling state that leads to aging in biological systems. And that's a bit of a handful. So actually, I think Jim just made a great transition to what I'm going to be talking about, which is a lot about diffusivity and anomalous diffusion. So the system that I'm going to be talking about is insulin secretion. And just a quick biological primer is basically if you look and you just eat one of these delicious brownies that we have outside, what happens in your bloodstream? So basically, immediately after, within 5 to 10 minutes, you get a spike in the insulin that's released in your bloodstream. And then over the course of the next 60 to 120 minutes, you get a sustained release of insulin. Unless you're diabetic, then this looks very different. And so people have always posed that there have to be two separate vesicle pools. So the first pool that creates this first rapid spike basically is already pre-docked vesicles that are close to the plasma membrane, and they get released really fast. And then there's the second pool that's for this long, sustained plateau. And we were kind of trying to investigate what distinguishes these two vesicles. And so let me give you a little bit of a primer on how these vesicles actually get to where they're secreted. Basically, they're transported towards from the intimate cell to the outside of the plasma membrane via microtubule-associated transport. So you have kinesin and dining motors, and they transport this huge insulin granule towards the outside of the cell where they dock, and then they get basically secreted. Okay, and that's all about biology. Basically, what we get from our collaborator in Robert Sharon's lab, we get these beautiful single particle tracking trajectories of insulin granules in the cell. And this is in 6 cell line, and you see these green dots. So basically, the insulin granules are labeled in green, and just for scale, if you look at the red, on the right side, you see how the tracks. The red ones give you kind of an idea of how big or how much space an individual track explores. And so I just picked 3 sample trajectories down here, and you see that they have very, very different morphologies. You have this, in the middle one, you have one that's stuck most of the time during our movie. On the left side, you have one that runs and then gets stuck and then runs again. And the third one is quite different again. And so we need a statistics approach to understand what happens to these vesicles in the cell. And so the question we were asking is, can you use statistics of these dynamics to basically understand something about biphasic insulin secretion? So let's go into something that should be very familiar. We use the mean square displacement. And so the mean square displacement is very commonly known. You use it usually to find diffusion constants and find scaling laws. You figure out if you have anomalous or normal diffusion. So I'm going to give you a quick primer on this for people who might not be as familiar with it. So we have the mean square displacement, and you see 2 variables there. You see t and delta. If you calculate the mean square displacement as a function of delta, it's basically your plain old what you see in the physics textbook to estimate the diffusion lag time. So you coarse-grain trajectory, larger and larger time steps, and you get a scaling law. Okay, and that's shown here for just plain diffusion. The other one is a little bit more tricky. Pick your favorite delta, usually pretty small, and increase the amount of trajectory that you take and analyze. And so in that case, if you have a pure diffusion, no memory, nothing changes over time. It really doesn't matter how long you measure your system. However, imagine you have a particle that's running around happily, and suddenly gets stuck somewhere, in place. If I integrate over this whole trajectory, the longer I include my trajectory of my mean square displacement is going to decay. And so suddenly this is not true anymore for anomalous diffusion processes that have any kind of correlation at the spatial or temporal level. So basically what you want to watch out for in my talk is like whenever we don't have linear and don't have a constant scale. All right. So here are our insulin trajectories, and I just reported this from a published paper from our group. Basically on the left side you have the scaling. You see that the scaling is 0.8. So you have subdiffusion. You're slower than a normal diffusive process. On the right side you see this is known very near constant. And the scaling is minus 0.3. And so I'm going to highlight most of the right side because that's interesting for our process. If your mean square displacement as a function of measurement time is not constant, in some fields it's called aging. So it has nothing to do with biological aging. You're not getting older. It kind of says that your system gets like slowed down. So that's where this analogy comes from. And it indicates that you have these long-lived traps, which I presented before when I was wiggling my hand here. Okay, so we were trying to understand this in more detail in the postdoc in the lab. Basically, we made this very phenomenological model where you have a cell, which is a circle for physicists, and you see these green trajectories basically inside the cell. Your insulin granule moves in a correlated random walk. This is, uses a continuous time random walk to be specific. And as soon as you reach one of these hotspots on the outside of the cell, you can get secreted. If you simulate this for a set of parameters, you basically get this nice biphasic secretion pathway. There are two things that are nice about this model. You get the right secretion pathway, but also we found that aging is absolutely required. This decay in the mean square space is absolutely required to get this sustained plateau on the right side. Okay. But it's kind of not quite right because we're assuming correlations inherently. We still don't know where these come from. We just assume that you have a correlated random walk inside of the cell. So now let's get one step closer and look at the molecular transfer. Okay. So we zoom in and we look at an explicit modal filament model. And I'm just going to highlight a few features of this model. It's a very plain Newton integration type thing, where we have these we have filaments. They have a directionality because microtubule transport is directional. And you have a motor, and the motors basically can have multiple filaments, can attach to multiple filaments by multiple binding sites. And then we have some distance-dependent probability to attach to these filaments, and the panel C is kind of a key point. We enforce that you have to walk on a filament. That comes directly from our data. If we correlate the trajectories with the filament network, we see that motors always walk on filaments. And then basically you make your step and you simulate this on a random. What happens? Well, we were very happy when we saw this graph. Basically, our simulations give us a wide range of scalings. So if you tweak our parameters, you basically can go from subdiffusive to superdiffusive, and you can get aging in all sorts of conditions. And I was really happy because if you look at the red graph, it's exactly the scaling we get, the combination of 0.8 subdiffusive scaling on the left side and a minus 0.3 scaling on the right side. And we were happy, but we still didn't know where this aging came from. We know we get it, but where does it come from? And so we look at these individual trajectories and we see this cycle. We have a motor, and it gets into basically a closed loop of filament. And it runs in a circle, and circle, and circle, and circle, and rarely ever gets out during those simulation times. And so this was really, really exciting because suddenly we can understand where do these traps come from. The motors get stuck in these traps. And so we can make this much simpler. We go to an idealized geometry, we have a square lattice, and we basically run the motors from that, and we see exactly the same thing. And if we actually explicitly write this down, it's really nice. If you have 90-degree angles, this model is like really, really beautifully simple. You can write down an explicit master equation. You can actually numerically solve it exactly, and then you get this kind of vortex-like streamline structure inside this vortex. And so then we can actually use this master equation. We introduce absorbing boundary conditions outside of the vortex in this diamond-shaped form. And we propagate a probability distribution in this vortex, and you see it a couple of time steps down there. You see how it runs around in a circle. And then eventually, it will decay completely to a stable pattern. And so if you look at the survival probability in the vortex, this is basically if you have absorbing boundary conditions, you lose probability throughout that. And that's basically the analogy of our particle leaving the vortex at some point. So first you have a constant because you need a finite time with a finite motor that makes a finite step. You need a finite time to reach the boundary and reach the absorbing boundary first. Then you have a power law decay time where you basically lose probability in a power law fashion. And that corresponds to basically our probability distribution cycling in this vortex. We see that very beautifully. And eventually you get a stable pattern. As soon as you're in a stable pattern, you just get exponential decay out of the pattern. And so this was really nicely because power law survival times are associated with long-lived traps, are associated with aging. We were really happy about this. And so we looked back about other people who suggested things of how you can stall motors. And there's a very, very fundamental and very beautiful model, the Untitled model. The Untitled model, just for intuition, is exactly what you think it is. Basically means that motors are dragging on something and they're stalling each other out, and that's how you can pause, where motors don't move anywhere. This model is basically one-dimensional because you only need one filament and two motors that go in different directions, and they can stall each other out. We are suggesting something that basically requires at least a two-dimensional network, if not a three-dimensional network, where you basically have the dimensionality. You have basically this closed-loop structure that is required. You can't do this on one-dimensional film. So we compared what kind of scaling would you actually get from type 4 one. So if you compare this, the dashed line on the right, I just want to highlight that basically there's no aging in the type 4 one because you get only exponential trapping times. We get power trapping times much longer. And then we can actually make a prediction about if you change the number of binding sites. So for example, you have granules that have hundreds of motors associated with them versus granules that have 10 motors associated with them. They're going to have very different aging properties. So you basically can, hopefully, find somebody who's going to verify this prediction in an experimental setting where you can actually tune the number of motors that are associated. And then we also get a prediction for the lag time exponent that's not as strikingly different from the time of 1. So I'm just going to quickly finish up with a little bit of biological speculation. If you think about a cell, you have this beautiful cytoskeletal structure inside. And it's very complicated, and it's very, very intricate, but it also changes over the lifetime of the cell majorly. You have a polarized cell, you have an unpolarized cell. It goes through all the spindle rearrangement during division. It's never the same. So the cell can very easily and fast rearrange the cytoskeletal structure to trap motors in certain places where they might be needed soon. And so we're kind of hoping that this might be a really good explanation for how you get these biphasic transport, for how you get motors localized in certain regions of the cell, basically zipping them along more line filaments, and then you trap them in this region where you have this very, very dense network. And I think this can be a very general model. We've also seen this in our collaborators' data of actin networks, and so if you have a system that shows this kind of thing, I'd be happy to talk with you. And with that, for the theoretical work, I want to thank my advisor, and 2 postdocs have done the major insulin work, and then Norbert Scherer and his students who have given us the insulin data. And this project was funded by Mersak, and I'm funded by HMI. So thank you.
Can you ever rejuvenate cells?
Sorry?
Can you ever rejuvenate cells?
So, actually, this is interesting because aging is a process that happens to the granule. So this cell is completely happy over hours. So these motors eventually escape. So if you look at a single trajectory, it gets stalled, and then over a really long time, which are longer than our measurement time, usually it gets out, right? So in that sense, yes, there is no finite time where you're just sitting there forever and ever. It's not. And clearly we had this exponential tail, so eventually you're gonna get out of these vortex. Yeah. I cannot help you with longevity, though.
Can I come back? I mean, so you suggested that some cellular event would actually release these trapped motors. Is there any evidence of that?
So in this case, it's really like the people have this phenomenological picture. You have the pre-doc vesicles, they get out. And then because these are trapped for long times, you can actually secrete over 2 hours, which is a significantly longer time. So this is basically, that gives you a characteristic time of how long they spent in these vortices cycling. So they don't get released in any artificial way, they just eventually get out of this vortex. But completely synchronized, and that's how you get this long, non-sustained plateau of release.
Over here. I didn't catch it. Do you average over multiple trajectories? Can you distinguish between a trajectory that has dynamics that's subdiffusive and 2 populations where one is completely static and one is diffusive?
We have done the following thing, which is very similar to what you're suggesting. We can sort trajectories by their curvature. And then we get different populations that exhibit different aging exponents. We don't explicitly look at subpopulations and their scaling because we have a numbers problem at that point.
Yeah. So I have one question. So what is the size of this granula? And so what is the size of this granula? And do you have an estimation how many motors attached to this granula?
What's the size of the vortex?
The particles.
Of the particles?
Yes.
They are like 10 to 20 microns, I want to say. Sorry, they're 200 nanometers. These guys are about 200 nanometers. nanometers.
So do you have an estimation about how many motors attached to these particles?
There is a rough estimation. It kind of depends a little bit on your cell line that you're using. Our collaborators say they have between 10 and 15 kinesins and dyneins. They can't distinguish the two.
Do you think you could relate any pathologies in this type of aging to any type of diabetes? So any diabetes could be related to issues with the microtubules or transport?
There are people actively working on that. We are less involved in this because the aging part, so the sustained transport is still okay in diabetes type 2. The spike is what you're missing if you look at the profile. We don't actively work on that, but I think people are investigating this.
All right, if you found anything you heard today interesting, why don't you take one more for dinner? All right, let's take them all again.